Okay, here's a fundamental definition for this section. We're going to consider a finite set of states, S1, S2, up to Sn. So basically we're taking some population and breaking it up into n parts, right? So every element of the population has to belong to exactly one of these n states. And we're going to let Pij be the probability that a thing in state J will move to living in state I. So Pij is the probability. It's the probability that a thing will move from state J to state I. So if Pij is a probability, it has to be a number between 0 and 1, right? 0% chance that it happens means it definitely won't happen. And then 1 means 100% chance that it will happen. 0.5 means 50-50, right? So a probability, any probability, right? When you study probability theory, any probability is some number between 0 and 1. And then the other thing is the probability that a thing will move from state J to state 1 is P1J. The probability that a thing will move from state J to state 2 is P2J. P3J, right? This is PJJ. So the probability that a thing will stay put. And then the probability that the thing will move from state J to state N, that's going to be PNJ. So each one of these individual probabilities, if you add them all up, you have to get 100%. Because every member of the population has to live in one of these things at any given time. They might move from one state to the next, but when you add up all the states, you just get the sum total of the population. So that's a really fundamental principle behind all of this. So when you add up all of these probabilities, the probability that I will move from state J to anywhere else, any one of these n states, 100%. So when I add all of these things up, I'm going to get a 1. So now we can arrange the Pij's in a matrix. This thing is called a probability matrix. So all of the entries are between 0 and 1. And then P1J, so for example, P12 plus P22 plus blah, 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 plus Pn2 is equal to 1. So P12 plus P22 plus blah, blah, blah plus Pn2 is equal to 1. In fact, if you sum along any one of the columns, you're going to get a 1. So this is the thing that, right, these two properties make this square matrix a stochastic matrix. So what is a stochastic matrix, to review? It's a square matrix representing the probabilities that a thing will move from state J to state I, right? All of those probabilities arranged in a matrix. All of the entries have to be between 0 and 1 because they are probabilities, and because everything has to live in exactly one of these states, everything in the column has to sum to 1. In other words, there's a 100% chance that you will move from state J to exactly one of these things. So memorize that definition of stochastic matrix, 2 parts. All the entries are between 0 and 1, and when you add up along the columns, you will get a 1. All right, really quick, we just want to check and see which one of these matrices are stochastic. So first of all, if they're not square, then they're not stochastic. So we'll confine our study of stochastic matrices to square matrices. Whether they are or aren't, they will always be square for us. So which of these are stochastic? So everything, all of the entries are between 0 and 1, so check. And then when you add up along all of the columns, you get 1. So let's write down what this means in terms of moving from one state to another state. So the fact that it's a 2 by 2 matrix means that there are 2 states that we are looking at. P11 is 0, P12 is 1, P21 is 1, P22 is 0, right? So there's a 0% chance that I will move from state 1 to state 1. In other words, there is no chance that anything living in state 1 will remain in state 1. So what does that mean? If there's no chance that a thing will remain in state 1, then that means it has no choice. It has to move to state 2. So going from state 1 to state 2, right, if this thing is a 0, this has to be 100%, right? So moving from state 1 to state 2 is guaranteed. Moving from state 1 to state 2 is guaranteed, right? The probability that a thing will stay put in state number 2, again, 0%. So if nothing in state 2 is going to remain in state 2, that means everything in state 2 has to move to state number 1. So that means there's a 100% chance that we will go from state 2 to state 1. And so here's a diagram of what this matrix is representing. So when you see these diagrams, then you know how to write it down in matrix form. We'll see an example of that in a bit. So what about these two? So all of the entries are between 0 and 1, that's good. If you add up along the first column, you get a 1, that's good. But if you add up along the second column, you don't get 1, right? In fact, it looks like you get something smaller than 1. 2/3 is smaller than 3/4. And so 1/4 plus 2/3 is going to be smaller than 1/4 plus 3/4, which is equal to 1. This column is fine. So because this column does not equal 1, right, does not equal 1, this is no to the stochastic question. And then the same thing here. All of the entries are between 0 and 1, but when you add up along the first column, for example, you get 0.6, right? So here you get 0.6, not equal to 1, so this thing is not a stochastic matrix.